So if one discusses the concept of ECG, what is ECG? ECG is basically a record of the electrical activity of the heart. So not the mechanical events, rather the electrical events. Anyways, so whenever depolarization is happening or repolarization is in the process of happening, there's basically the creation of electrical potential differences in the heart, because part of the muscle will be depolarized and part of the muscle of the cardiac muscle will be repolarized. So the charges at the outside of the heart or at the inside of the lumen, they will be different and there will be electrical potentials. And so what will be the direction of the potential? Now this is very important. It will always be from the negative to the positive. Always. This is very important. Now, what do we mean by negative? Negative is basically referring to the part of the cardiac muscle that is depolarizing. Because when something is under the process of depolarization, we're talking about any excitable cell, there is a reversal of polarity, the inside becomes positive, and because of that, the outside becomes negative. So the outside body fluids, doesn't matter which one we're talking about, will become negative, right? And where there is basically the cardiac muscle fibers are still in the polarized state, the inside, because of RMP, will be negative, the outside will then be positive. And so there will be electrical currents generated in the body fluids, and because the body fluids in the body are excellent conductors, some of this electrical current will be transmitted to the surface of the body, and you can sort of register it with electrodes. And we have different electrodes and different leads, and that will make sense. So if you talk about an ECG paper for now, anyways, if you talk about an ECG paper, they will be thick vertical lines like this, right? And there will be thick horizontal lines like this. And so this is the kind of graph you will be getting, and this is kind of important. So you will have these boxes, and on the y-axis this is basically 0.5 millivolt. So if this is say 0, this is minus 0.5, this is plus 0.5, and this is plus 1.0, whereas this will account for about 0.2 seconds. So 0, 0.2, 0.4, and this is time, whereas on the x-axis, whereas we have electrical potential differences or voltage on the y-axis in millivolts. Now we will also have thinner vertical and horizontal lines, no worries about that. And we will in the vicinity of one box or within one box, we will have 5 smaller boxes, 25 in total actually. 1, 2, 3. My apologies, I've drawn this a bit too much. This is very uneven, so let's start from over here. 1, 2, 3, and then 4. 1, 2, 3, and then 4. Whatever, these should generally be even. So 0.2 divided by 5 is basically 0.04. This is important. They ask you that suddenly. So how much time does one small square mean? That's basically 0.04. How much millivolt? That is basically 0.1. 1. Oh, I'm so bad at this. 1, 2, 3. Yep. 1, 2, 3, and 4. So basically, we have these big boxes made up of thick vertical and horizontal lines, and one big box accounts for 0.2 seconds and 0.5 millivolt, and in each big box we have 25 smaller boxes, and basically each small box accounts for 0.05 second, which is 1/5 of 0.2 second and 0.1 millivolt. Now drawing a standard ECG record or an ECG finding often comes up. So what are the parts of an ECG record? We have waves, we have segments, and we have intervals. And waves are basically deflections. So the first deflection that tends to appear is the P wave. And P wave, how much duration does a P wave have? It is about 0.1 seconds, which is 1/2 of a big square, so 2.5. So if we kind of like do this, right, and this is it, and the amplitude tends to be 0.1 to 0.3. This is a P wave, and this is because of a certain electrical event that is happening in the heart. It is atrial depolarization. Because of atrial depolarization, not because of the depolarized heart, but because depolarization is still happening, part of the heart has a different potential, the other part has a different, so there is a potential difference which is recorded in this manner, and this is showing the amount of time it takes for the whole of the heart atria to be depolarized. The way this happens is that the depolarization of the atria and of the heart, basically it starts at the sand, which is near the opening of the sinoatrial node. So at any point or at the most time period, this part is more electronegative compared to this part, because these are depolarized and these parts are not for most of the time period. So as I mentioned, vector is from negative towards positive. So why does this have a positive deflection? That will have something to do with the leads, which I will get to you shortly, right? So this is the P wave showing atrial depolarization, a potential difference. Right, now we have a bit of a time period in which there won't be any deflection, because during that time period the atria will be completely depolarized and the ventricles will be completely polarized, so there won't be any potential difference, and this tends to last for about 0.02 to 0.06 seconds. I'll go for 0.06. This is a normal interval. However, if it crosses 0.1 seconds, meaning it's either this much or more than that, this period of non-deflection, that's abnormal, and that means something. So what does this represent and what is it called? This is a segment, and you should know segments are basically isoelectric lines in the ECG, and this is basically representing AV nodal delay, because after the whole of the atria have been depolarized, spread in this direction and spread throughout, this is basically an interatrial band, and then there are fibers anterior, middle, and posterior. They're going to the AV node. So they are the internodal fibers, anterior, posterior, thoral, I guess. This is Bachman, and the middle one is Venki-Bach. Anyways, after this has been done and it reaches the AV node, AV node has a very slow rate of conduction, and it is itself not as such excited, and even though it is a bit excited, the electrical potential produced because of it is so small it is not registered, because it is a very small muscular mass, and the amount of potential difference that is produced has to do with the muscle mass. Anyways, it basically delays it for a time period of like as I've said, it does delay it for some time, about 0.16 seconds, and this has something to do with this interval. So this basically represents all of this whole thing represents the amount of time taken when impulse is being transmitted from the atria to the ventricles and has not yet reached the ventricle. So all of this is the PR interval. This small part over here is the AV nodal delay, right? And this is the time where the atria are depolarizing but have not fully depolarized. At this point, the atria have fully depolarized. So this was the P wave, this was the PR in segment, and this is the, all of this including the wave and the isoelectric line is the PR interval. Right, now if this is prolonged to greater than point, all of this is prolonged to greater than 0.2 seconds, it basically means that there is some sort of a problem in the AV node. It's delaying the signal for more than it has to, it needs to, so there may be a block at this point. There are actually 3 types of AV nodal blocks. Now something else happens. At this point we have a very small negative deflection known as a Q wave. Why it is negative, I'll tell you later. And this is representing again a depolarization, this time of the ventricular septum. Of the ventricles, because the Purkinje fibers have this direction, the septum is the first to be depolarized. This is something that lasts for about 0.02 seconds, so half of a small square. This is Q, then we have a large positive deflection that is at least 4 times as large as this one. So, and generally it's about 1.5 millivolts. And I made a mistake. This is 0. This is then minus 0.5. 0.51 and 1.5. Anyways, it's very big, so it's kind of like till here. And this tends to last for 0.04 seconds, complete 0.04 seconds. So over here then. So R wave is representing the depolarization of most of the ventricles, especially the apex, all of the ventricles with the exception of the base. And the base is this part over here, and the last bit to receive the depolarizing signal. So then we have R, PQR. Now R is the one that is representing the depolarization of the base, and this is again negative. Now this is representing the whole of the depolarization of the ventricles, this QRS complex. And if this is prolonged, now this is normally about 0.02, 0.08 seconds. Now if this is prolonged, it means that there is something wrong with the spread of the depolarizing. It's taking too long, might be because of dilatation or hypertrophy, could be suggestive of that. Now after this we have another interval. This is the QT interval, and then we have the T wave, which is basically 0.27 seconds. Now we will have another segment and another interval, the QT interval and the ST segment. Segment is just the isoelectric portion, and the interval in total covers about 0.35 to 0.45, so I'll go with that. 0.35 minus 0.08, it's basically 0.3 minus 0.03, 0.27, I guess. I'm so bad at this. So 0.27 means that it's basically going to have whole of this part over here, 0.24, and if we are assuming this is like almost 0.26, right? This is it, and they're saying that the interval in which there is basically T wave is 0.27, right? And this is the QT or the ST segment, so this is going to be pretty big. So 0.235 to 0.45 is the whole of this interval. This is 0.08. The T wave is then 0.27, so we will have one big block and like almost 2 of the smaller from the other one. Then we have the T wave. This is pretty big, but this is wrong. And why is it wrong? Because the QT interval doesn't include just the first one. Unlike the previous one we did, it also includes the T wave. So if it's total 0.35 to 0.45, and we know that the T wave is about 0.27, and we kind of have to also know that this is like 0.08. So 0.08, it's 0.35. Anyways, if it's 0.45, it can be in certain situations it might disappear altogether. So we make a bit of a distance over here. This is 0.4, this is 0.6, and then we have 1. This is 1, and then we have 0.27. And this has about the same height as the P wave. So this whole QT interval, the QT interval has two waves, the QRS complex, which itself has a duration of 0.08, the T wave with a duration of 0.27, and a segment which is basically the QT segment or the ST segment is very important in certain diagnosis. It is about 0.10. This is how it normally is. Now you would have expected, what does this mean? This is atrial repolarization, and why isn't it negative? You would have expected, my apologies, ventricular depolarization. You might have expected deflection because the electrical potentials ought to have reversed, because what is depolarizes first ought to repolarize first as well. But in the case of the ventricles, this is not the case, and I will tell you why. This was AV nodal delay. This was ventricular depolarization. This was when the whole of the ventricles were depolarized. The whole of the ventricular mass was in a state of depolarization, but this depolarization was somehow held for some time. But because it was still depolarized and there wasn't any electrical potential, you didn't get any electrical potential change, but all of this was still depolarized. Then we have repolarization, which does last for some time, right? And this is when, and during the whole of this time period of 0.35 to 0.45 seconds, the muscle is in systole. So during the whole of this period, contraction is happening and muscle and the aorta is being filled. Not exactly the aorta is being filled, because part of this will be isovolumetric, but basically the ventricles are contracting throughout this period. This is when the ventricles have fully depolarized. This is when the ventricles have started to repolarize, but contraction is still happening. And after this period, this is sort of a bit of a variable period. It's when both atria and ventricles are relaxing, and its interval is based on the heart rate. It is the one that is most highly affected by heart rate. The one segment, these are not as affected. They're more constant, at least in terms of motion, but this is very much affected. And depolarization. Now atrial repolarization, why is it not shown? It's because it happens at the same time as when ventricular depolarization is happening, and because the curve is smaller, its activity is largely obscured. Additionally, it is negative, as you would expect it to be. Now what about this? Why isn't it negative? The reason for that is you would expect the septa to repolarize first, and so you would expect a vector like this, but it is not like this. Why? Because the spread is from the endocardium to the epicardium, so it's from under to above. But because during the whole of this time period, including the repolarization phase, the ventricles are still contracting, and so the inner parts are really depressed, and coronary circulation to those parts are depressed, and so they don't repolarize first. Repolarization starts from the surface and largely from the apical surface, and so you get a positive deflection. So onwards to the next part.